take a sphere and disassemble it into finitely many pieces. The Banach-Tarski Paradox guarantees, by means of a mathematical proof, that you can reassemble the pieces into two copies of the exact same original sphere. How is this possible? Let's start with a circle of radius 1 and remove 1 point. Is there any way to rearrange the circle so that we could cover this point? Well, you could take some other point on the circle and move it over, but then that just leaves another gap in the circle. What happens if we move another point to fill this one in and keep repeating this process? Will the circle ever be entirely covered? There's no way, right? There should always be 1 point missing. But consider what we've done to the circle by removing a point. Since the circumference of the circle is just 2 pi, remember the radius is 1, in essence, the circle has now become equivalent to a segment of the real line that includes the point 0, but does not include the point 2 pi. And if you consider the function that takes any point in this interval to the following point in the xy plane, we indeed get the entire circle back. The reason this is possible is because there are an uncountably infinite number of points that make up the interval. So by removing just 1 point, we still have an infinite number of points available to map onto the entire circle. Keep this example in mind, as the Banach-Tarski Paradox will apply the same basic idea to a sphere that has been broken apart and rearranged with some parts missing. We will need to find a clever way to map what's left of the sphere to cover any gaps that seem to appear. Let's now consider a full sphere of radius 1. There are an infinite number of rotations we can apply that all preserve the symmetry of the sphere. And not only are there an infinite number of rotations, but there are also an infinite number of different poles we could rotate around. But for our initial purposes, we just need to pick any two that are perpendicular to each other. So we'll pick these two and label them as x and z. The counterclockwise rotation around x we'll label as A, and the counterclockwise rotation around Z we'll label B. The respective clockwise rotations will be A inverse and B inverse. Now before proceeding, we'll need to take a short detour through a bit of abstract algebra and set theory. Here we have a set that has just two elements, the numbers 1 and -1. If we further consider the operation of addition, then by adding 1 to itself, we can form the number 2. And adding 1 again, we get the number 3, and so on. If we now add -1 to 1, we get 0. And if we further consider all the possibilities of adding -1 to itself, then we can produce the entire set of integers. In this case, since -1 is just the inverse of 1, and the set is closed under addition, the integers form a group. Another way of describing this is to say that the group of integers is equivalent to the collection of all possible sequences you can create with the numbers +1 and -1. This is what's called a free group. And anytime +1 and -1 are next to each other in a sequence, they will just equal 0. So the free group will be all sequences consisting of +1, all sequences consisting of -1, and the number 0. So the integers are just the free group of this set. Now let's go back to those rotations we defined on the sphere. We can also form the free group of A and B. This will consist of all possible sequences that contain the letters A, B, A inverse, and B inverse. To visualize this, we'll change the opacity of the sphere and consider a single point. What happens if we take a sequence and apply these rotations to the point? So first, rotate by A, then rotate by B, and finally rotate by A inverse. We get to another point on the sphere. Now what about if we apply a different sequence? We get to an entirely different point. Notice that anytime we apply A or B, and follow it up by applying its inverse, the two cancel out and we get back to where we started. So taking this into account, anytime we have this occur in the middle of a sequence, we will just cancel it out. And to be complete, we will also represent the path of just doing nothing by the letter epsilon, standing for the empty sequence. Taking all this into account, the set of all possible combinations of the rotations A, B, A inverse, and B inverse will consist of the empty sequence together with all sequences that begin with the letter A, which will denote by S of A, and all sequences that begin with the letter B, and similarly A inverse and B inverse. So the free group on A and B will be the union of all of these sets. Now we would like to make sure that all of these sets are disjoint. That is, that no sequence in one of these sets is also in another. But how can we ensure that they are? In particular, how do we know that we don't have some really long complicated sequence that ends up bringing us back to the point we began with? So we might end up having lots of sequences that are really just the empty sequence. Well, in general, this could be the case. But there's one way we can ensure we don't have a problem. So far, I've been talking about general rotations A and B around these two axes. But let's now pick a specific angle to rotate by. Theta equals arc cosine of 1/3. So A will rotate by arc cosine of 1/3 around the x-axis, and B will rotate by this angle around the z-axis. And A inverse and B inverse will just do the reverse. We can even represent these rotations as matrices as well. The reason we choose this angle is because it's an irrational multiple of pi. That is, it's produced by multiplying pi by another irrational number. This ensures that the path traveled by any sequence, no matter how long, will never go back to itself. So all of these sets are truly disjoint. Any sequence you find in one will not be in another. Okay, so now let's take a closer look at what the sequences in S of A actually look like. Any sequence here will begin with A, and then there will be 4 possibilities. It could be followed by no letter, or it could be followed by another A, or a B inverse. It will never be followed by an A inverse though, since the two would just cancel. So this means that a sequence in S of A will either be just an A, or an A followed by a sequence starting with A, or an A followed by a sequence starting with B, or an A followed by a sequence starting with B inverse. Now let's reduce all these expressions by multiplying by A inverse everywhere to cancel all the leading A's. We get that A inverse S of A equals the empty sequence, S of A, S of B, and S of B inverse, which is almost the entire free group, right? We just need to add all sequences starting with A inverse. And now we've got the whole thing. This means that by just taking 2 subsets, so only those sequences that begin with A and those that begin with A inverse, and rotating the first one by A inverse, we get the entire free group. And we can do the same thing with sequences beginning with B and B inverse. So by considering 4 subsets of the free group and applying the A inverse rotation to one of them and B inverse to another, we have effectively doubled the points we are considering and have made 2 copies of the entire free group. Let's now visualize what this looks like on the sphere. The free group of A and B, when applied to a specific point, will cover a countably infinite number of points on the sphere. It won't cover the entire sphere, however, since the sphere consists of an uncountably infinite number of points. All these points that get hit is what's known as the orbit of our starting point. In fact, all of these points that have been hit will have the same orbit, so starting again from any of these will result in the exact same points covered. So we've successfully duplicated a section of the sphere. Now how do we duplicate the rest of it? In order to do this, we need to make use of a simple yet controversial mathematical axiom called the axiom of choice. The axiom of choice is one of the 9 axioms that form what's commonly accepted as the foundation of mathematics. This axiom tells us that any collection of non-empty sets, no matter how small or large, has a choice function. So this means that even in the case of having an uncountably infinite collection of points, like all the points that make up a sphere, there is always some way to choose a point. And this is the case even if we can't come up with any specific rule for how to choose those points. So by accepting the axiom of choice, we are now in a position to duplicate the entire sphere. all we need to do is to pick any point that's not in the previous orbit and apply the same process of duplication of the free group. And then repeat this for an uncountably infinite number of points until the entire sphere is covered. Or rather, almost the entire sphere. There's still a problem with poles. Anytime we begin with a specific point and apply rotations around two axes, the poles of both axes never move. So they are not duplicated through this process. Here is where the problem at the beginning of the video comes in handy. Remember when we showed that a circle with a point missing can still be mapped in a clever way to cover a full circle with no points missing? Well, since every point in the broken circle gets mapped to a point on the full circle, we can also think of this as equivalent to just rotating the entire thing by some angle. We'll need to take a similar approach here. In this case, for each pole, we just need to find another pole that does not intersect it. Then there will be some angle by which we can rotate about this axis to get rid of this hole. And repeating this for every pole, which again there will be a countably infinite number of, we cover the entire sphere. So this results in a duplication of the entire surface of the sphere. However, the full version of the Banach-Tarski Paradox says that you can duplicate not just the sphere, but the entire solid ball. This includes all points inside the sphere down to the center point. Well, that's not a problem. We can just repeat this same process, and instead of applying rotations to points on the surface, we can apply them to lines going down to the origin, but not including the center point. You can see that applying any rotation to a point on the surface will turn out to be the same rotation for any other point on the same line inside of the sphere. At this stage, the only thing that's left over is the center point. Once again, we can use our broken circle technique. Here, we just need to create a circle that is inside the ball and intersects the center point. By applying a rotation, we can cover this hole too. So there you have it. The entire sphere has been duplicated. One sphere has become two.